So in this video we're going to solve this classic RC circuit. I'm going to write down the expressions of the circuit, come up with the differential equation. I'll present the result, and then if that's all you want, you don't have to watch the rest of it, and then the rest of the video I'll be solving the differential equation using the classical techniques. So just to explain this circuit, this is a DC voltage source, this is a capacitor of some capacitance C, and there's a resistance. There's always a resistance in a real circuit, and when you do this kind of analysis, if you don't have a resistance and you have an ideal voltage source, you can end up with very intractable problems. So it's always good to have a resistor, even if it's very, very small, when you're doing this kind of analysis. So we're only interested in the point in the behaviour of the circuit once the switch is closed. So using Kirchhoff's voltage law, we can write down the equation for this circuit. So we can say Vs is the volt drop across the resistor, that's here, that's IR, plus the voltage across this capacitor, V out. Now we don't have a direct expression for V out, that's what we're going to try and work out. But the way we have to get there is we have to form a differential equation, because the only thing we do know about the capacitor is that the current that flows through the capacitor is C dV out by dt, where V out is the voltage across it. So we can substitute that into there, and we get Vs, using this one, is C dV out by dt R plus V out. So just rearranging that ever so slightly, we can write CR dV out by dt plus V out equals Vs. So before presenting the solution, we'll just have a little sketch of what we expect to see based on how we know capacitors and resistors work. So if this is time and this is V out, the voltage across the capacitor, then we expect at time 0 that voltage to be 0, and then as the current flows out of the source through the resistor into the capacitor, we expect that to rise up to the maximum voltage it's going to be, which is just the voltage from the supply, because there's no current going anywhere else. So that voltage there is just Vs. Similarly, we expect the current flowing in the circuit when at time 0 the capacitor is empty, so that's just a short circuit, so the current that's flowing in here is just the supply voltage divided by the resistance. So, and then as the capacitor charges up, we have here, so this maximum current that flows here is just Vs over R equals I max. So having said that, that's what we expect the solution to look like. I'm now going to present the solution, which is here. So if that's all you were looking for, there we are. So we can see if it makes sense compared to what we expected. After a lot of time has elapsed, this whole expression, this part, will decay to 0, and this will just be 1, so the output, the voltage across here, will just be the supply voltage. And the current, initially at time 0, this will be the maximum value, Vs over R, and then after a lot of time has passed, this current will decay to 0. So that fits with what we were expecting. So the rest of this video is going to be presenting how we solved the differential equation, which, for the purposes of making it easier to follow, the differential equation was this, wasn't it? So the rest of the video will be how we solve this differential equation to get this expression at the top. So how do we solve this differential equation? Well, there are a whole host of ways we can do it. I'm going to use the techniques that I was taught at university, and this book has been very useful. I haven't done it for a while, so I can heartily recommend this book for all sorts of things, particularly if you don't want to have to revisit Laplace transforms every 5 minutes. So let's write down what we're going to solve. So we're going to solve over here. CR dV out by dt plus V out equals Vs. So what's the process for solving this kind of differential equation, ordinary differential equation, first order? So the multi-step process. First process is we find the solution to the complementary function and that's an easier problem to solve, and I'll talk about that in a moment. And then the second step is to look up the expected form of the particular integral, which for the kind of problems we tackle here in electrical engineering are quite simple. Then we're going to substitute, if I can spell right, substitute the complementary function, or substitute the candidate solution into the original differential equation. And then we're going to find the value of the particular integral. All of these steps will become clear in a minute. And at the end, the last step is using initial conditions, which I'll tell you what they are. We can solve for the constants. So in our circuit, we know that the initial condition V out at time 0 as a voltage across the capacitor, as soon as the switch is closed, is equal to 0. We could also use other initial conditions which are equivalent to the same thing. For example, we know that I of 0 is Vs over R, but that's not what we're going to do here. Right, so we're going to work through these steps for our expression up here. So step 1, find the solution to the complementary function. So what's the complementary function? Well, we have a differential equation up here, but it has what's called some forcing. So it won't decay to 0 because it's being forced with some constant input here. So what we're going to do is we're going to solve this equation, but we're going to say the right hand side is 0. So we're going to solve this expression. How are we going to do that? Well, we're going to just rearrange it slightly. We're going to write it as CR dV out by dt is minus V out. Then we're going to divide through by CR. So we're going to have dV out by dt equals minus V out over CR. Then what we want to do is we want to get the variable V out all on one side again. So we're going to divide through by V out. This is leading to what's called the separation of the variables, which seems to be a bit of a hack. Right, so now we can integrate both sides with respect to dt. So if we come up here, I'm going to start here. So if we integrate dV out by dt 1 over V out by dt is equal to the integral of minus 1 over CR by dt. We can see that these dt's cancel, and we're integrating 1 over V out by V out. And we should remember from our A-level maths that 1 over something integrated is the log, and if we integrate over here, we're just going to get t, and then the constant of integration from both sides we're just going to represent as k prime. So let's make that a bit nicer, get rid of the log. So we're going to take the exponential of both sides. So then we're left with V out equals e to the minus t over cr plus k prime, which is e to the k prime e to the minus t over cr. We're going to represent this as just k. So the solution to our complementary function is V out is k e to the minus t over cr. And we're going to call this C here for complementary. This is the solution to the complementary part. So that's part 1 of our multi-step process up here. So now let's do part 2. So we're going to look up the form of the particular integral. Now this is just something you have to look up in textbook. But for these kind of problems it's very simple. We've got a constant. So our solution, because our expression, our original equation has this particular form here, and we know this is a constant and we're just a first order equation, we know that the solution to this kind of problem is our complementary plus our particular. Yeah, so this is what our solution is going to look like. So our solution is so we've yet to determine V out particular and the value of k. So the next step is, how do we determine the value of V out particular? So we're going to go up here, and we're going to write it up here. So the way we do that is we substitute our candidate solution, and I'll just write it here again. This is our candidate solution so far. So we're going to substitute that back into our original equation up here. To do that we need an expression for dv out by dt, so we're going to differentiate this. That's going to be minus 1 over cr times k e to the minus t over cr, and we know from the table of results that when our forcing is a constant, our particular will take on a constant, and when you differentiate a constant it goes to 0, so that's just it. So now we've got, in this expression here, we've got V out, which is this bit, and we've got dV out by dt, which is this bit. So we can write it all out as CR times minus 1 over CR k e to the minus t over CR. That's the first bit, plus V out, which is k e to the minus t over CR, plus V out P is equal to Vs. So you should be able to see that we've just substituted the things we've got so far. Now this bit on the side rather conveniently cancels, so CR cancels with that, minus k e to the minus t over CR plus k e to the minus t, so that all goes to 0. So we're left with V out P is equal to Vs. So our solution is coming together quite nicely now, and the solution so far for our differential equation is k e to the minus t over CR plus Vs. So we just now need to find this value of k from the original constant of integration. So how do we do that? We look at our list, what we've got to do. We've got to use the initial conditions. So the initial condition that we know is that the initial voltage across the capacitor V out at time 0 is equal to 0. So if we set that in that expression, we go 0 equals k e to the minus 0 plus Vs. So that's 1, because anything to the power of 0 is 1. So we've just got K equals minus Vs. So if we substitute this value of K back into here, we've got Vout equals minus Vs e to the minus t over Cr plus Vs, which we can write a bit more intuitively as Vs 1 minus e to the minus t over Cr, which we've already seen from the slide earlier is in fact the answer. Now what about the current? Well, that is just this expression. So if we just differentiate this, so C dv out by dt, we've already done it. dv out by dt is just going to be Vs over Cr e to the minus t over Cr. This bit disappears, and then to get the value of I, we just do C times this, so we get Vs over R. And there you have it, the solution to the RC charging circuit with a series R, and you're interested in the voltage across the capacitor.